Okay, so as I mentioned a couple of videos ago, we can rewrite indefinite sums using what's called sum identities. And that's what we're going to focus on here, is just understanding the basics of sum identities. Now, I'll go ahead and tell you, in this class, the entire semester, this is one of the hardest concepts to understand. So it's going to take practice. You'll probably get frustrated. So be sure you ask questions and you actually try to work out some problems on your own. You're not going to get better unless you actually try. Okay, so an identity is just simply a statement that allows us to rewrite one expression into another form, and that helps us to solve and rewrite problems. So, I got 5 identities here. You need to practice with them, and when it comes down to it, we're going to actually start combining some of these identities to start rewriting some of these sigma notations. The first one's called coefficients come out. So here, f of k represents my sequence that I'm trying to add up. C is just some coefficient. Could be a positive, negative, fraction, decimal, doesn't matter, but it's a coefficient. Coefficients get to come on the outside. So if you have a coefficient on the outside of your sequence, then just bring it on the outside of your sigma. It might seem a little confusing, so let's do an example. For example, here, if I want to find the sum of this sequence right here. Well, 4 is a coefficient. Based on this rule, it gets to come on the outside. So I can rewrite this sum notation. My starting term stays the same, so k equals 1. It's still an indefinite sum because I don't know exactly where to stop. But I know the coefficient, based on this rule, gets to come on the outside, and the k is going to stay on the inside. So, while that doesn't look like it did a lot, it actually is going to help as we start learning more of these identities. So let's keep going. Our next identity is called the sigma of a sum of 2 sequences is the sum of 2 sigmas. Sounds like a tongue twister, but essentially what it means is if I have one single sigma and I'm trying to add up 2 sequences, then I can split that up into 2 separate sigmas. Okay, so let's do an example. Here I have an indefinite sum. I'm starting with the first term, going to the nth term. Again, it's indefinite. And this represents my 2 sequences. My first sequence is 2k. My second sequence is -1. Well, based on this rule, since I have the sum of 2 sequences, I can split it up into 2 sigmas. So let's do that. Alright, so I have my starting value, our starting term is k equals 1, and I'm going to the nth term. And based on this rule that we just learned, that's an ugly looking sigma, let's try it again. I have 2 sigmas. Based on the rule, I have plus in the middle. And my first sequence goes with the first sigma. My second sequence goes with the second sigma. Okay? Well, now let's go ahead and start practicing using as many identities as we can. So, I don't yet have a rule for -1, but I do have a rule when I have a coefficient on the outside. So, remember, we just said that coefficients come out. So, this sequence, based on what I know so far, can be rewritten into the sigma, starting with the first term, going to the nth term. Coefficients come on the outside of k. And this guy, he just stays the same because I don't know any other identities yet to help me there. So plus sigma from k equals 1 to n of -1. So far, based on these 2 identities that I know, this is as much as I can rewrite my original problem. Again, it doesn't look like much, but again, we're building baby steps to come up with what's called a closed form definition. Okay, so by the end, once we have all our identities, this will be really useful. Our next identity actually can be done 2 different ways. It's called add a bunch of 1s, and it's all based on what term do you start with. If you start with the 0 term, then when you add up a bunch of 1s, that sigma just becomes n plus 1. If you start with the first term and you're trying to add up a bunch of 1s, then it just becomes n. These are 2 separate identities that essentially do the same thing. It's all based on what term did you start with, the 0 term or the first term. So here I have an indefinite sum. I'm starting with the first term and I start off trying to take the sum of two sequences. Okay, so I want to use my previous identities that I've learned to split this up. So again, my first term to n, first term to n, plus in the middle. My first sequence goes with the first sigma. My second sequence goes with the second sigma. Now what I want to do is apply as many of these identities that I can. So again, coefficients get to come out. So I'm just focusing on this sigma alone. The 3 gets to come out. Okay? Now for this one, I don't have a rule to add up a bunch of 2's, but I do have a rule to add up a bunch of 1's. If I start with the first term, a bunch of 1's becomes n. So what I need to think about is how can I rewrite 2 so that I can apply this rule. So, and I'm going to call this sigma k equals 1 of n of 2 times 1. Because we know 2 times 1 is 2. That's an easy trick, no big deal. Now, since I have a rule for 1's, I can pretend that this 2 is a coefficient. And remember from our previous identities, coefficients get to come out. So this piece can be rewritten again as 2 sigma k equals 1 to n of 1. That piece is written as much as it can be. This piece I didn't do anything else, so it's just going to fall down as it is. And then plus just stayed in the middle. So for now, our original series that we were trying to find can be rewritten as this. Again, we're just using these sigma identities to help us rewrite these problems because it's going to help us later on. As we add more identities, we're going to be able to go farther and farther and farther. Take a baby steps. Our next identity is called Think Gauss. Gauss was a German mathematician. He's really famous. I really strongly recommend you Wikipedia him. He did lots of cool things. Arguably one of the best and most important mathematicians of all time. So if we're adding up a bunch of numbers, then we can rewrite that as n times the quantity n plus 1 divided by 2. So we're going to use that to apply it to this definite sum. It's a definite sum because I know exactly where to start and I know exactly where to stop. And this is one, if you paid attention to the previous videos, you can actually use your calculator to calculate this since we know exactly where to stop. So let's start applying some of these identities to rewrite this series. Again, I have the sigma of 2 sequences, so I can rewrite that as the sum of 2 sigmas. And again, that's an ugly sigma, so let's rewrite that. Our starting value was the first term for both of these sigmas, and we're going to the 100th term for both of these sigmas. Now, the first sequence goes with the first sigma, so 1/2 k. The second sequence goes with the second sigma, so 2. And again, we have many, many identities that we've learned so far. This is our 4th identity, so we're going to go as far as we can. Remember, for this one, let's do it in green, coefficients get to come out. So I'm going to rewrite this as 1/2 sigma from the first term to the 100th term of k plus, just falls down. And this one is very similar to what we just did in the previous example. I don't have a rule for the sum of a bunch of 2's, but I do have a rule for the sum of a bunch of 1's. So if you recall that, I can rewrite 2 as 2 times 1 and think of 2 as a coefficient. And coefficients get to come out. So 2 sigma from the first term to the 100th term of 1. Okay. Well, we want to keep going as much as possible. So this one, 1/2 just falls down because it's a coefficient. It's staying on the outside no matter what now. Now, we just had a rule that said if we're adding up a bunch of numbers, it's n plus 1 divided by 2, where n is our number on the top. So we're going to call that n, or sorry, 100, 100 plus 1, and all of that divided by 2. Now, since all of this is pretty complicated, I put it inside the big parentheses here. Okay, now plus just falls down. Again, we're going to, the coefficient for our second sigma, it just stays on the outside. And we just had an identity that said to add up a bunch of 1s. Okay, so a bunch of 1s, when we started with the first term, it was just n. And remember, n is on top, so this time it's just 100. Now, we can use our calculator and clean this up, or we could clean it up by hand, whatever we want to do. So, I want to do order of operations. Remember, you take care of parentheses first, so 1/2 stays on the outside. On the inside, I have 100 times 101 divided by 2. And then plus 2 times 100 is 200. Pretty easy, no big deal. Now, I'm definitely going to use my calculator to help me out here because that's a pretty big number. If I can find my calculator. I think I closed it down, so let's open a new one. Sorry, technical difficulties, but here we go. All right, so again, I want 100 times 101, which is 10,100. Now divided by 2 on the inside, which is 5,050. So on the inside here, I have 1/2 of 5,050 plus 200. Okay, so now 1/2 of 5,050 is 2525. Plus 200. And that's 2,725. So, since I had a definite sum that I was trying to find, I knew exactly what term to start with and what term to stop with, I was able to actually use my identities and go all the way down and evaluate that series, find the sum of the sequence that I was trying to originally do. Came out to be 2,725. Now, if it was an indefinite sum, I would have to stop. I wouldn't be able to go all the way down and actually plug in. So, there's a difference between definite and indefinite sums. One more identity. This one's called, think Euclid. Euclid's called the father of geometry. He was an ancient Greek guy. Again, he's another one of those mathematicians. I strongly encourage you to go back on Wikipedia. He did lots and lots and lots of stuff. Arguably the most important mathematician. Okay? So, think Euclid. It looks kind of complicated, but all you got to know when you're finding the sum of the sequence, what you need to do is you need to know R and you need to know what N is. If you know that, then you just plug into the formula. And it's not that bad. It looks complicated, but it's really not. So let's try an example. So I want to go from the 0 term to the 5th term, and I want to evaluate, I want to find the sum of this sequence. Well, first off, let's actually write out what this sequence is, just for practice. So I want to start with the 0 term. So everywhere I see a K, put in a 0. Now, I go to the first term, so 3 to the first, to the second term, to the third term, to the fourth term, and finally to the 5th term. I started at the 0 term and I went to the 5th term. Okay, so this is a sequence. Again, it's just an order list of numbers. To find the sum of the sequence, which is called the series, we're just going to add these numbers. We could obviously just type this in our calculator, and I encourage you to do that. Just kind of double check my work that we're going to do. But instead, I'm going to apply Euclid's rule. So, based on the sequence, this is just scratch work. Based on the sequence, R is 3 and N is 5. And I'm going to plug into my rule up here. So, once I know that, I can use my rule. I'm sorry, my arrow should have gone down here. So my series can be rewritten as 3 to the 5 plus 1 power minus 1 all over 3 minus 1. I want to clean this up as much as I can, so I have 3 to the 6 minus 1 all over 2. Well, let's use our calculator here. So I have 3 to the 6 minus 1. So my top is 728. On bottom, I still have divide by 2. Okay, so now let's do that, divided by 2. So 364. Now, if you went through and actually typed this in like I asked you to, the series, if you did this by hand, is also 364. So, since I had a definite sum, I was able to apply Euclid's rule into this formula. I knew my R, I knew my N, and it's kind of like a shortcut method. Now, it's not too much of a shortcut because that's easy to type in. It just takes a little bit of extra time. So we've gone through all 5 identities. Now what we're going to do is do a couple of practice problems on coming up with what's called a closed form definition. Again, take some time, make sure you understand these identities, and like I did in this video, try to make up some examples where you have to use multiple identities at the same time. And that's what we're going to focus on in the next video.